Welcome back to The Explainer. Today, we're jumping straight into a foundational text on systems modeling, specifically decoding the whole language of MIMO and SISO systems. So let's get right into it. Okay, let's dive into this. The absolute biggest engineering challenge we face when analyzing real-world environments is just the sheer chaotic volume of interacting variables. So how exactly do engineers and scientists effectively map and actually control these crazy multi-layered architectures? Well, this question right here is our starting point. We've kind of got to funnel our perspective down, going from this overwhelming macro-level chaos all the way down to a super precise, manageable micro-level model. We literally need a systematic way to take all that complexity and just, squish it down into a functional, solvable format. So our source material categorizes these systems mainly by their input-output complexity. First up, we've got the rather intimidating reality of MIMO, multiple input, multiple output, or as you might see it in French, plusieurs entrées et plusieurs sorties. This basically means you're tracking a bunch of inputs affecting a bunch of outputs all at once, which creates this massive tangled web of cross-coupled interactions. Yeah, it's a lot. But conversely, we have the total relief of SISO, single input, single output, or mono entrée, mono sortie. This completely streamlines the whole architecture. Literally, one variable goes in and one variable comes out. It's a highly efficient, straight-shot pathway to evaluate system behavior without dealing with all that cross-channel interference. Now, to build a really strong analytical baseline, the text intentionally narrows our focus strictly down to SISO systems. And honestly, don't worry, this is a good thing. By stripping away all those multiplexed variables you get in MIMO architectures, we can focus entirely on the core mechanics of a basic system. Because think about it, once you definitively nail down the fundamental relationship between a single input and a single output, scaling up to multivariable systems just becomes an exercise in iterative logic, rather than having to learn a completely new paradigm from scratch. Now, what's really interesting about this slide is how it serves as the ultimate visual anchor for our analysis. Look at how it captures a complex operational state using just a simple directional flow, right? We absolutely don't need some crazy detailed schematic of a physical circuit or like a mechanical linkage to understand the fundamental process here. This simple block elegantly distills the entire story of a dynamic system into three basic things: an input, a transformation, and an output. So let's break down those specific variables step by step. We start off with U of t. This represents the input to our system at a very specific instant in time t. That feeds directly into S, which represents the system itself, the actual mathematical or physical transformation that's going on. And finally, Y of t represents the output of the system at that exact same time t. Now, the inclusion of that t parameter, that is absolutely crucial. It grounds our whole model in the time domain, which is a great reminder that we're evaluating dynamic, continuous processes. The transformation S is constantly operating on an active input to give us a real-time output. And this brilliantly illustrates the operational notation, Y of t equals S, bracket, U of t, bracket. Honestly, this mathematical equation is basically just a simple sentence stating the output is the direct result of the system acting on the input. That's it. It takes our conceptual diagram and turns it into an active algebraic relationship. This is what actually allows us to compute system states and then smoothly integrate this specific module into much broader control algorithms down the line. The source text makes a point to highlight that we use this specific operational notation strictly pour souci de simplicité, or for the sake of simplicity. It totally standardizes the link between what goes in and what comes out, without forcing us to draw out a visual flow diagram for every single calculation. Nobody wants to do that. By formalizing the system into this super clean shorthand, we strip out any ambiguity. We're handing engineers a streamlined tool to analyze mathematical behavior. In this context, simplicity literally equals operational efficiency and absolute clarity. So, we've taken real-world complexity, abstracted it into a focused SISO model, visualized its flow, and translated the whole thing into functional operational notation. But let's take a step back and consider the broader implications here. If S represents just one single discrete process, what exactly happens when countless S blocks are linked together? Like, what if the output of one block cascades directly into the input of the next, using block diagram algebra to form some massive, closed-loop control system? Well, by mastering this basic SISO building block in today's explainer, you are actually unlocking the exact mathematical framework you need to engineer and model the most advanced control architectures in modern tech. So definitely keep that framework in the back of your mind as you scale up your designs.